Hello everyone, this is our CSCI 430, our operating system, and today we move on start a new topic. So this one related to the operating system. So when we move on, we need to know what's the internal or the design principle. Okay, so if we want to design a correct routine of the control the concurrent activities, in the coming few slides we'll talk about what's the concurrency. Okay, or thinking if we need to design, make sure all the process by working together, like for the concurrency, then I will provide like a better like a management. So how can we solve it is the most difficult aspect of the system programming. So the ad hoc technique using by the programmers like in the early programming and also the real-time system. Okay, when we talk about the real time, of course, right now, so we kind of like solve the problem, right? So although, so like always the notable of like the subtle program server, like whose effects could be observed only certain relative like rare sequence of action occur. So here, and the errors are those that are particularly difficult to locate since the persist condition under which they appear very hard to reproduce. Here kind of things that when we talk about the OS, okay, the design. When we start to talk, of course, we talk about the multiple processes, right? We talk about multiple processes or even the multi-threads, okay, all this. When we um, need to like design the operating system, so we need to concern about one thing is how can we manage all these processes and then the first, right? So we did discuss about like what's that multi-programming. Okay, sometimes we talk about multi-processing. Okay, and also the multi-threading, okay, it's a kind of similar. And also how about like the distributed like processing all this. So all this we going to cover. And when we talk about multiple, okay, multiple process, okay, multi-programming, okay, multi-processing. So here's the things we will need to discuss concurrency, okay? But we need to think about that. So there are three difficult like contexts. First one is the multiple applications. Um, if we have multiple applications we need to running, okay, maybe you are very hard to imagine if I'm telling you, okay, if you, let's say in normal when you open a browser and then if you want to play a video, okay, or music on the YouTube, and then you want to open your VS Code, writing some programs, and then maybe you need to open a PDF like Word document, okay. Without the multi-program, we need to like finish one task by another task and then open one application. That means that either you need to stay on the browser, let the YouTube finish the whole music, then we will start another one, let's say open the VS Code programming, okay? And then once we finish this part close, then we can start to open the PDF. But it doesn't make sense, right? Because when you running an application at that moment, you cannot do other tasks. That's why we need to support multiple applications. That means we can switch. Okay, multiple programming was developed, okay, at that time to allow switching between multiple running program. So that's why you can feeling, okay, currently simultaneously, okay, how can you playing, listening to music? You can work on your working on your VS Code and then look at like scroll down, checking your guidelines on PDF. Okay, so that's how it works, like switching between multiple running programs. Okay, and then once how about the structure applications? Because some of application they're more likely like designed naturally, as I said, like concurrent process. Some of them maybe not. So how can we talk about it? Or when we talk about the multi-threads or multi process, okay, if some of the applications they didn't really structure design for that, then we cannot really utilize, okay, the CPU or the whole performance, right? Also, how about your operating system structure? So this like usually include the OS itself. Okay, so no matter the Windows itself, Linux, or we talk about the Mac OS. So here will be the different like context we need to think about for the concurrency. And so far, there's some like key terms. Okay, we need to know. Okay, later we will talk about like what's a deadlock, okay, or the mutual exclusion. Okay. Right here later when we need to have some question. Okay, if you remember there's a previous step, I kind of like skipped it that part because we are going to cover like and discuss about it. So for the atomic operation, we need to know is the function or action implemented as a sequence of one or more instructions. They appear to be indivisible. Okay, so there's no other process can see an intermediate state or interrupt the operation. It will be a, atomic. Okay, that means that it only itself. Okay, the sequence of instruction guaranteed to execute as a group or not execute at all. Either if you need to start it, you cannot be like stopped in the middle. So it's a whole set of sequence. Okay, and have no visible effect on system state. Okay, and also automaticity guarantees the isolation from concurrent process. It's called the atomic operation. Critical section is a section of code like within a process, okay, that require access to share resources that must not execute while other processes is in a corresponding section of code. So here the thing is like because we do have some shared resources. If you remember when we talk about the Sudoku, how can we think like make sure all those process like to access and then with those shared resources. Okay, so they must not be executed while other processes in the corresponding section of code. So this one is called a critical section. Okay, and sometimes if you see the um pseudocode, we say, okay, we are going to, after checking, and we execute the critical section. Okay, we didn't talk about it, but that means that we don't care about that part. It's like once you getting the right to the resources, then you can execute those critical section. Okay, and the deadlock. Okay, so here's the situation. It's say maybe two or more resources unable to process because each of them waiting for one or others to do something. Okay, um, none of them can be like move on to the running page, or they're waiting for each other's waiting for event, and we enter the deadlock. Okay, and for the live lock, that means like two or more processes continuously changing their state in response to change in the other process without like doing any useful work. Is called live lock. So we talk about a lock. So that lock is like no one can process. Live lock is they keep switching, but actually it's like doing nothing. Okay. And also the mutual exclusions, this one is the requirement that one process is in the critical section, the access share resources, and no other process maybe in a critical section that access any of those shared resources. So it's a mutual exclusion. So here's one of the requirement. Let's say if I say I have a situation, I have a question asking you how can you prevent the dialogue or like the mutual exclusion. So there's a requirement. So you need to fulfill this too. Okay. And also we talk about what's the race condition. So right here, the race condition is a situation in which like multiple threads and also process like read and write a shared data items. And then the final result depends on the relative like timing of their execution. It's called a race condition. So they might like waiting, right? Okay. And starvation, so it's a waiting for something in definitely like by the scheduler. So although it's able to process, but it never chosen. Later, especially when we talk about scheduling, okay, maybe we have some different mechanism, especially for OS, we are not using one mechanism. We adding the time so everyone, all the process can share, right? The CPU fairly, and then we adding priority because we want to let certain high priority interrupt that goes first. Okay, so because there's several mechanism, okay, working together, it turns out maybe there's some process, okay, certain task always they putting at the last. Okay, that means that you are the lowest priority, but always say putting in the last. So you always say starvation. So you never able like putting into a running stage. Okay, so here's the called concurrency possible issue you need to know. Okay, when we talk about concurrency. Okay, remember. And more ideas about what's the principle of the concurrency. So we talk about what concept, including the race condition and mutual exclusions right here. So the interleaving or like overlapping between them so can be viewed as example of concurrent process. Okay, so both like present the same problem here. when we have a unit processor, because the relative speed of the execution process like cannot be predicted, right? So really depends on the activities of other processes, also the way of like always handle those interrupts. Okay, the scheduling policy we talk about that later we're going to cover. So all these, okay, we just talking about the unit process. Okay, so because it depends how they handle it. Okay, each of the process. And when we talk about concurrency, because they're working together, then we need to think about if they are sharing the global resources. Okay, maybe the memory, there may be within certain data, all these. Okay, the difficult like for the OS to manage the allocation for the resources ultimately. Okay, and also this they is difficult to like to locate the programming error. As a result, they're not like deterministic and reproducible. We talk about like reproducible, like go through OS. So mainly here's a difficulty. Okay, so when we talk about the concurrency, and let's give you the example. Let's say a simple like race condition. So right here we have the procedure. Okay, so there's an in out. Okay, right in out, and then we have echo function. Echo right here. Okay, there's a void function. We didn't return anything, and when we get char, get an input, and then we get it, and then put it as an output, and then print char. Okay, put the char. Okay, put the output, and that's it. If we have a P1, okay, invoke echo. If we remember the sample code we're using, let's say fork function, okay, so we're gonna like interrupt immediately after the get char. Okay, so get char, get equal x right here, and then P2 invoke the echo. Okay, y, okay, again, and P1 resume, okay, x, so overwritten, and y output like instead. So it may cause a lot of things. It's called a race condition. Will it will be involve like P1 and P2, okay, and all these like P1 and P2 will cause the like in the echo because we try to get the interrupt because we're switching between these like processes, right? We have P1 and P2, and when we try to get the invoke the echo, okay, so we get we assume it's a X, okay, and then we have in a Y. Once we assume we only have, and it's just like overwritten because we are P2, and then we overwrite because we are sharing the one because so we're just waiting for it, okay. And for the race condition, it causes like when multiple processes or threads read and write data item. So here's the issue. The final result depends on the order of execution. Okay, so who lose? Okay, the loser of the race. That means in this case, is the process that like update latest. Okay, and then we determine the final value of the variable. So here's the situation. Okay, and for the OS concern, when we design, like what's the concern of the operating system when it design and manage those are issues raised by the existing concurrency. So the OS must able to do the following. First, keep track of the various like processes. They should able to locate and delocate the resource for each active process. Okay, when we loading an instruction, able to locate the resources to it, and after we finish, how can we delocate allocate the resources? Okay, then we can release. Otherwise, no, we have the situation later about like the times if you remember. So how can we make sure right here like those like maybe the deadlock, okay, or the live lock, or how can we make sure like we never have a mutual exclusion right here or starvation? Okay, so right here, that's like we need to prevent right here. Okay, and also we need to protect the data, the physical resources of each process against the interference like by other processes too. Yeah, and then we also need to ensure that the process and the output they are independent of the processing speed. Okay, otherwise it will cause a problem of the race condition. Okay, right here. How can we make it like independence like, of the speed? Okay, so maybe we have something like what the critical section. Okay, so later when we are designing it, then I give you some exercise assignment that you can think about that more in detail. Okay, so far I'm just giving you some like the processor interaction. And let's say if the we have the degree of awareness And if the process like aware of like each other's, then we cause the competition. Okay, because they don't know each of them. So the influence of like one process have on the other is like without one of process independent of the action of others. Also, the timing of process may be affected. Okay. What's the potential control problem right here? So the mutual exclusion, deadlock. Okay. Or there because there's some renewable resources like that, or a starvation, so they cause it waiting for it. Okay. So because they don't know each other. Also, the person indirectly aware of each other. Okay, if they have some like shared object. So because they maybe have some like cooperation by sharing, working together. Okay, share. So the result of like one process may depend on information obtained from others, we're getting from others. Also, the timing of a process may be affected. Okay, like this. So it will have like same mutual exclusion, deadlock, starvation. One is like the data coherence. Okay, here are things because we rely on the data information obtained from others, right? So we'll add one more potential control problem. And then next, one is the process directly. Okay, this time is directly aware of like each others. They have communication primitively available to others. So the third connection, they will cooperate by communication. Okay, they are really like talking to me. So the result of one process may depend. Okay, but here may depend on information from others. So it also have the timing of process may be affected. Okay, for this one, possible is the deadlock, even they are like communicating or because they have some like consumable resources, and then because the deadlock also starvation. So because you're waiting the share process like this. Okay, resources. So here's the like possible like interactions. Okay, okay. So you need to know like the one is unaware. Okay, each other's maybe indirect aware and also direct aware. So mainly like if they have unaware, it's a com competition. Okay, relationship. Or if they indirectly, then it's a cooperation. By the sharing. Okay, by sharing. And then if directly, that means by communication. Okay, so you need to know what's the potential control problem right here. And we talk about the resources competition right here. That means the concurrent process. They came into conflict when they are competing for use of the same resources right here. Some example, let's say we need to use the I/O devices. Okay, both of them they need to getting the keyboard input. Okay, maybe you need to use the output. Okay, or maybe you need to use the scanner, whatever. Okay, or this the I/O. How about memory? Okay, access to the memory. Okay, reading data, writing data. Okay, processor time. Okay, how much time can you use? The clock. Okay, the clock. The how much time? So right here there are three control problem. If you still remember, like the competition, correcting. When's the mutual exclusion? Okay, so it must be enforced, and also this enforcement also cause two additional potential problem. Once deadlocks and starvation. So right here. So there's a called a competition, right? So you know, and if you look at the example right here, we have the process. Okay, so later when you look at the pseudocode, and then how can we make it work, make all this like source code like better? Because when you look at the source code for the like P1, P2 until like Pn, okay. So most time we always start with the while condition and then true, okay. And right here when if you remember we talked about the critical section command, so we don't care what's the critical section because we are designing. Okay, so the preceding code in the beginning, and then we have the called the enter critical, okay, RA, okay, and then exit the critical RA, okay, right here different, okay, and then we have some for the code, and then we have the critical section. So all the process they are identical right there doing. Then how can we make sure the mutual exclusion? Okay, if you were still not yet quite remember what's the memorize what's the mental expression, just recall because it's like critical session, make sure we are like only one process to enter the critical session, right? Access the share resource. That means we have some share and one of it can enter and then to access it. So right here you say that we have all the critical session. Okay, so who can enter the critical session is the main idea. So what's the requirements like for us to doing the mutual exclusion? Okay, so first one must be enforced. Okay, if a process, okay, must do like so without interfering with other process, there is no affecting others. Also, no deadlock and starvation. That means that if this some process they waiting, then they don't cause a deadlock, they're waiting for nobody or starving, they're waiting, never executed. Okay. And also a process must not be denied access to a critical section when there's no other process using it. Okay. So if you're giving you the question when you are wait like the like checking condition or somehow enter, you will realize that if like none of it, even nobody using the CPU, nobody using it, and then none of it able to get into the processor, okay, then it will cause an issue. So they must not be denied, okay, and no assumption are made about the relative processor speed and number of processes, okay. That means when you decide, when we giving an example, looking right here, I don't care if there's only two process or like n process. Okay, they should be kind of doing the same because they will execute the same piece of code. We're checking the condition, and if we are able to enter the critical section, yes, then I don't know which one will enter first. And once we enter, we change the flag and make sure okay it finish the critical section, exit, turn it, and I don't know like P1, P3. P5, 6, 7, and which one, either one gain the critical flag. Okay, that can enter it. Okay, for the West, then we are keep waiting for that. Okay, so here's the idea. And also they need to like remain inside is the critical section for the finite time only. So we need to be careful. So here will be all the requirements for the military execution. Okay. And we talk about the cooperation by sharing. Okay, so if you remember, so it's that interacted indirectly, that part. So, and for example, let's say those like share of variables. If we have a read write buffer, okay, with the writer, those like problem. Later we will show you what's the with the problem. So we discuss about it. And suppose two items of data, A and B. So to be like maintain a relationship like A equals to B. If we want to do that, A equals A plus one, B equals B plus one plus two, B equals like two times B, and A equals two times A, like this. And then the next one is the cooperation by direct communication. Okay, the third one, so it's a message passing. So the primitive way of the for sending or receiving messages. So unlike all those before, like there's nothing like share. Because the mutual exclusion is not like required, but we need to be careful like how the deadlock and starving. Okay, starving can occur. So here's the differences. So so far just like quickly go through we say there's some example mutual exclusion, okay, problem, deadlock, starving, okay, starvation, okay, and then sometimes we call the data coherence or the competition right here. Okay, so here will be all the possible situation. Okay, difficulty right here. So you need to prevent. Okay, and when we move on, talk about more like the concurrency, is like cooperation. Okay, more. So okay, more details. Okay, what's the problems right here? So let's say we have like coordinates requirement. Okay, so if there's a like third program, so they work for the in the living of the first instruction sequence. Okay, and they're cooperating first, they inherited non-deterministic. Again, also they're non-reproducible. So far, okay, so they're really hard to debug unless they carefully design, right? So we need a design. There's one of the example machine really long because for the machine for the radiation therapies. Okay, so the software needs to control the electron, accelerator and electron beams, X-ray potential. So the software control the dosage. Okay, and if the software like errors like cause the overdose and then the death for the several patients, it's really possible. But so if a serious like waste condition on the shared variable or poor software design, so it will cause it the system error. Okay, so they determined that data like okay, speed during the editing. So what the key factor? So in production, the error condition. So if the prescription, okay, they're like at the fast pace, then the overdose that occur. So if they fast, then they overdose. Okay. So here's the thing: is the coordination. Okay. And there was some called the space shuttle example. Okay, we have like the space. So the original space shuttle launched like about 20 minutes before the schedule launch. Okay, So it's just a five like computer, okay, 1, 2, 3, 4, and then one is BFS. So the fourth one is a primary avoidance software system pass, okay. They are synchronized and they are running in real time. Okay, so they once off the control system and result like the synchronize and compare like 440 times per second. Okay, and then the fifth computer is the BFS, is the backup fight system. So it will stay like synchronized in case that is needed. Okay, and also it written by computer different teams. Okay, then pass. So they're not say pass and then BFS. Then the countdowns are brought because the BFS disagree with the pass. Okay, so this equals the problem like the pass and then the BFS. So there's a like 1/67 chance that the pass was out of the synchronous one cycle, and because the bug due to a modification in the initialization code of the pass, because there may be some like delay in the initial request placed into timer queue. Okay, as a result, so if a timer queue not empty at the expected time to force use the hardware clock. Okay, so the bus is not from doing the extensive simulation. They may be doing simulation, they never, but once they reload, it causes problem. And then it makes the original space shuttle launch about like 20 minutes. Okay, here's the things. Because you don't agree, because they're not synchronous. And we talk about the atomic like operation right here. So we need to understand a concurrency program, then we need to know the underlying atomic like operation. Yeah. So if for the automation operation, we talk about an operation. So we always say runs to completion or not at all. Okay. And it's indivisible. Okay. So it cannot like stop in the middle stage and cannot be modified by someone else in the middle. It cannot. Also, it's the fundamental like building block. Okay. If we don't have any automatic operation, they have no way to thread to work together way. So kind of think about that. And mainly on most of the machines, memory references and assignments, like including load, store, so work there atomic. Okay, so we are thinking. So here is really important. Sometimes if you see a question asking what's the example of the atomic action, load and store, because we cannot say loading a content or data from memory into somewhere and then stop in the middle. Okay, because when we're reading into a buffer, okay, so we have to read in a whole complete, okay, data. Okay, so that's why it should be atomic. Okay, so we cannot stop in the middle. So it's more important. But there are some machine level instruction are not atomic. Let's say the double precision floating point store. So they're often not atomic. Also the VH or IBM 360. You never heard about that, but there's some. So they have an instruction to copy a whole array. Okay, so that means here's a different part. So you need to have a idea and concept, like what's the atomic operation, everything we discuss, we they say rely on it. And also we have the multiple like computation, including the first we're talking executing in parallel to like maybe they're sharing the resources and or some or like they will share the data too. Okay. Okay, they are fine grains, they're sharing. So when we increase the concurrency, of course, when we increase the concurrency, that means we're sharing more, then we of course will provide better performance. But however, it will cause a more like complex issue. Okay, billion keep switching. Okay, and causes grand sharing. That means it's like simple to implement, but it causes a low performance. These are things. So we maybe share a database like at the row or like table like granularity. Okay, right here. So we need to think about that. Like it's a trade-off. Okay, so if we choose the which way to do the sharing, then we need to give up. Okay, of course there's some advantage and disadvantage. Then of course like based on situation, then we will choose which one. Okay, and what's the motivation? Right here, there's a question. Okay, it's a good discussion when we talk about. Okay, so it's called too much milk. Of course, thinking. So yeah, it's a when we talking about OS. So energy between the problem in OS and problem in the real life. Okay, we think about that. So you need to think. So it can help you to understand real life problem better. Also, for the computer, like what's the stupid than people. So you think. So then people need to coordinate. So if you see a question, okay. So just like thinking is the process or person A, it doesn't matter. Okay, if let's say we have a time a start from 3, right? Okay, so we look at fridge, our milk. So we leave for store, our at the store. Okay. Actually, this is like what the process A doing. Okay. And then person A. So for person B, okay, you also look at the fridge and then you see, okay, out of milk. Okay, okay, I need to buy the milk. Okay. So we'll leave the store. Okay. But in this moment, you already buy the milk. Okay. And then when you arrive at the store, person A already arrive home and put the milk away. Okay. And then person B already buy the milk. Okay. And then they arrive home, put the milk. So right now you have two milk. Okay. So that means that right now, if we have the resources or access, okay, we need to have one. Okay. BDM, then checking, and then what is your critical section. So if you don't have any notice. Let's say if we have a question as for person A, I go out, okay, I try to buy a meal. How can I let others? Maybe you have person B or person C. Okay, check. If I know you already leaving for store and buying the milk, then I'm not going out, right? So does it make sense? Yes, right. So here's the thing is called synchronization. Okay, so one thing is that we need to know is the using atomic operation to ensure all the cooperation between the threads. So for now, like we say the only loads and store the atomic. So we will show that it's hard to build anything useful, like we only read them, right? So let's say if we are checking, okay, let's say we load and we put, then it's called a synchronization right here, atomic operation. Okay, is it possible that two people like going in and the meal or bring the email? So here's a kind of example. What's a critical session? So what will be the critical session for here that we cannot stop? Okay, so the piece of code that only one thread can execute at once. Okay, so what's the possible part? It can be the critical session. Also, like mutual exclusion. Okay, so how can we ensure only one thread execute the critical section? Okay, so only one thread execute, like, and the others like well doing its task. Critical section and mutual exclusion, they're two ways of describing the same things. So just like be sure when we describe it is. Then, of course, we can say, okay, let's put a memo, okay, to reminding another people, others if I leaving to get the milk. So here one example is like using a lock, okay, a lock. So we were using a prevent like someone for doing something else. So we lock it before enter critical section, right? And before accessing shared data. So when we lock it, once I get access, I lock it, make sure I'm the only one, okay, using it, using the enter the critical section, access the shared data. And after that, after I finish, I will unlock it. So once we are leaving, okay, so others can access those share data. If it's locked, then we will wait for it. Okay, so all this like idea, all the synchronization involve like waiting. Okay, so we need to like waiting for it synchronize. Okay, so how can we fix it? The meal problem by putting a lock on the refrigerator on the fridge. Let's say we lock it and take the key if we're going to buy milk. How about doing this way? Okay, so when I check, so if I'm going to buy, then I will lock it. Fix too much. Okay, right here. That cause like guarantee. Okay, so the roommate angry if like they only wants the orange juice. How about this? Okay, too much. Of course, we don't know like how to make the lock yet. Okay, in this moment, which I think how about like make it work better? If you say this time I don't want to buy the milk but orange, then this kind of things. Okay, but at least the lock can help. Okay. And then we need to think about, okay, how about need to be careful about the correctness of concurrency program. Okay, right here, because this is non-deterministic. Okay, so we always need to write down design behavior first. Okay, impose like say to start the coding first, and then when it's not doesn't work, pull the hair out like this in that thing first, and then code. Okay, it's important. So what's the correctness property for the too much milk problem? Because we never more than one person buys, right? We don't want to have more, or like someone buys if need. Okay, here's the things. Then we restrict ourselves to use only the atomic load and store operation as a building block. So that's what we say loading, and then the storing, right? That's what we're saying. Okay, maybe here's the possible solution, so you can watch it. So we can maybe use a note. Okay, it may be like similar idea is the unlock. You say, okay, to avoid buying tomato. Let's say we need a note before buying. kind of idea, right? So we can remove after we um after buying, so we can like have unlock. Okay, if you see the note, then don't buy it. So it's a waiting stage. So here's the idea, and later you will see more examples or the source code is applying this idea. Then suppose a computer like translate this one. So this one only maybe let's say the memory reads it right as a atomic. So in the beginning, we check, is it no milk? Yes or true. Later if you have some pseudocode, you can write it in this way. Okay, so we check if we say no milk, okay, and then I will see, okay, do we have a note? Yes. Then we will leave a note right here. So write down note. Then we will go to buy a milk. Okay, buy the milk, come back, remove the note. Okay, then done. Then you're thinking if I'm a person A, right? I will check. But actually, there are some other problem issue. But in this moment, just think about that. Okay, we're checking the note, right? So no note. Okay, just no note. Then I will leave the note, and then I go to buy milk, and then come back and remove it. So person B come. Okay, let's say if you in the stage is like okay, you already leave the note, and in the process, like critical section is that buy milk, right? Buy milk, and process B and check. Okay, there's a note right here, so I'm not doing anything. I will just wait until you remove the note and check. Okay, what's the result right here? So here's the thing, it's like still like too much milk, like, but it's only occasionally. Okay, right here. So because like we have roommates Alice and Bob over here, but no milk, no. So in this moment, I check like no milk, no note. And I say no milk, no note. And I say leave note, buy milk, remove note, and then I will go back to leave the note. So right here, the thread also get context switch after checking milk and note. So, but before the leaving note. So here's the thing, there's just still some issue, right? Because we have multi-threading, okay, multi-process, and then multi-threading. Okay, so right here, multi-thread. So here's a causal issue. So the solution makes the problem worse since it fails at intermediate. Okay, then what happened? How can we do that? So okay, so it will make it really hard to debug. Okay, if this I check the where I execute for the first process, so I say that person A, okay, I check no milk, no, and then why now I switch to person B, okay, no milk, no. So they all still fulfill. And then why not even you try to leave a note in this stage, and then are you going to leave a note? Right? So it's a problem. So it make it worse. So we must work like despite what the third side this pressure does, right? Then how about can we make it better? Okay, let's say, okay, how about let's say clearly the note is not like quite blocking enough, right? How can we fix it by placing a note first? How about this? Otherwise, I will leave the note. Okay, so I will see if no milk and then no note, then buy the milk. So after we buy the milk, after we execute, then we say we move the note. Then how about this one? What happened? And for humans, you're thinking, okay, I leave a note right here, and I will check, no milk, no note, okay, nobody writing it, and then I say, okay, I will buy the milk, and then after I come back, I will remove it. Okay, so far like this. But for the computer, maybe there no one ever buys meals, right? Okay, here's the things. If you remember, we talk about condition. So version one, we cannot like one of the situation right here. If you remember the table, because we need to make sure. Okay, so make sure we are at least there's some process like executing, right? So we cannot let them. Otherwise, call that like we cannot letting the CPU idle, nobody taking action, right? So right here, so you need to remember. Let's go back to this part. Then we say, how can we like make it looks better? Okay, so here is the second solution, like right here. So if we leave the note before checking, so we say, let me leave a note. Okay, leave a note. Okay, I will check if checking this. How about process B? Okay, let's say, do they have a note from B? If no, then I will going to check. Okay, do we have milk? No, then I will buy it. And then if no, I will remove a no. How about this way? How about this solution? Do you think it works? Does it work? Actually, there's a possible. like neither the first are buying it, right? So when you leave a note, and then third party also leave a note, and then finish, because say, okay, so there's a note right here, so nobody buy it, so B is not going to buy it, and then come back here. Also, third party also going to like leave a note. So you say, okay, there's a note right here, so I'm not going to execute. So it turns out it's like, okay, it really like unlikely this would happen, but sometimes at the worst possible time it really happened. So it caused, okay, no, none of it could cause the execution like this, right? So that means like this solution is still not yet perfect. Okay, so always thinking like each other. I think I'm not getting a meal because you're getting it. Okay, so this one. So it caused a the lockup is called a starvation. Okay, so it caused a starving. Okay, everyone is waiting for it, but nobody taking action. Okay, waiting for it. So how about the third solution? Okay, can we have like possible like two nodes solution? Okay, first I will leave a note, and then I will keep checking. Okay, if the node like node B does it exist or not? No, if I will do something, and then if we can find, okay, let's say we know that another process, okay, already have a node, we just say keep waiting in the loop. Okay, we are not do anything. Okay, unless the not be, okay, we move them in false, then we can go to check, okay, do we have milk? Okay, yes or no. Okay, if no milk, we're going to buy the milk. And after we finish the task, and we move note. Okay, and for this part, okay, so I will also like getting a leave note, and then getting the like checking, okay, how about processor A? Okay, and this like does it putting a note? If yes, then we can avoid situation, right? Does it work? Yes, both they can guarantee one thing, they can save to buy, or others will buy. Okay, so okay to quit. So like this way. So at least like we can perform in this way. So at X, this point, okay, so we say, okay, if no node B, then it's safe for A to buy. Otherwise, you're waiting and then find out like what will happen, or someone just keep checking. At Y point right here, so if like no node J, then B is kind of safe to buy. Otherwise, A is either buying or waiting the B to quit, or somehow like this way. So it's like right here. So the solution like in the number like three, okay, like last one, this one like protects a single critical section pieces of code. So this one is like, okay, no milk, buy milk. Okay, this one is the third, the critical part, and this one works, but it's like really unsatisfactory. Okay, so it's like really complex. Even this like simple, but we're like checking each other. Like we need to make sure, okay, this one is a process A, this is a process B. If you want to like swap the same identical source code, okay, the complex, right? Even this like we say it's a simple in the example, but really implement, how can you say, okay, you have to commit that way? It really works. And also, its code is different from B. Then how if there's lots of threads, right? So I say, what happened? So the code will be have slightly different of like for each thread. Okay, while A is waiting, also it's also consuming CPU time. So it's like busy waiting. Okay, you keep checking, but you wait. So do we have any better way? Okay, to do that, maybe have like hardware provide a better that means a high level like primitive, then like atomic like low install, or build even a high level programming like abstraction on like this new hardware support. So maybe it will be better. Okay. And so far, if we need to talk about like what's the high level pictures of it, so maybe the abstraction of the first is good. Okay, we should like maintain the sequential execution model. Also, how can we allow, okay, the simple parallelism, okay, to overlap the I/O or computation. Unfortunately, but I think they're still too like complicated little as a stage share between different threads, right? So when we think about the too much milk, this example, so the implementing a concurrent problem, okay, programs, okay. So only load and store because it like will be tricky. So also they are like our problems, right? So we will like implement a high level operation on top like atomic operation. So provide by the hardware, let's say. So maybe color synchronize the toolbox, and we can explore more like some common programming like per like this way. Okay. And how about, let's say, I think this one later you'll see more examples. So we have the form solution. Okay, so this one. And kind of the last part we're going to cover. Okay, so will be the suppose we have like some sort of implementation of the lock. So maybe more in a moment. Let's say we have the lock occurring or the lock release. So this will wait until the lock is free. Then we grab it. If we like release it, then it's unlock. So we're waking up like anyone like waiting. So this one. So it showing one thing is they all these they should be the atomic operations. Okay, if they're two first, they are waiting for the lock. Only one succeed to grab the lock. So here's the problem. See, okay, first I will try to like the milk lock right here, like a query over here. I try to get the grab it. Okay, there's a function. I try to grab it. If I can grab it, I will check. Is it no milk? Yes, then I can buy the milk. After I buy milk, I release it. Done. Once again, here the session code like between here is also between it also is the critical section, right? The critical section is a check do a milk and buy milk. So only one person can do it. Is a critical session. But this time instead of if we compare it with solution 3, right here we checking anything nodes and then or like checking while not. This time is better because we don't want to stay in the like called the busy waiting. Okay, we don't want to have a busy waiting. How about just like okay, so we adding it free. So once like, we check it's free, then we will grab it. So it will be better. Okay, it's way better than just like doing the busy waiting. And so far quickly cover this part, and for the next one, next one we will move on to talk about the mutual exclusion was the hardware support. And thank you so much. We'll stop by right here.